So I'm just gonna quickly run through data engineering and business intelligence. So the overall point of this particular session is I don't want to go too technical. I just want to give you guys an overview on what is business intelligence and what is data engineering, how it is different from data scientists or data analysts, and there are like I have to be honest here that there are like good money here if you guys are focused on having a nice car, nice house, and good salary. This is one of the jobs like you would actually get paid decently. At least now, no one knows about the future. So I think it's kind of like an area if you guys wanted to explore and see if you would fit into it. So today's agenda is gonna be we'll start with the introduction about myself, and we're gonna have 60 minutes on data engineering, and we have 5 minutes on business intelligence. I've given very limited time on BI because it's mostly visualization, so you would really understand it when if we speak about it in a real world problem. And the last 5 minutes for question and answers if you have any. So I'll try to keep it within the time limit, and then if it exits, we can try to catch up. So about myself. Vidi, as Radha ma'am introduced, I am an ex-MIT fella. So I finished my course in 2007, and I joined Accenture as a developer, and slowly moved on from on databases to big data eventually, and started working more on Hadoop and building lots of data warehouses for companies like JP Morgan, Dunn Stores. And then I moved to Facebook for a while, and then currently for Eagle Alpha as senior data engineer. It just sounds like a job interview because I'm giving out more about my background. So one piece of advice for guys who are in MIT, if you ever have an area, don't worry about it. When I joined MIT on my third semester, I went to my dad and said I had 5 cup, and he was so proud of me. But it's actually course under pending, so I had 5 areas. So actually, I loads at least 2 dozens of them. So life has changed since then. Like if you have an attitude to achieve something, you will achieve. So if you have like, it doesn't mean that I'm encouraging you to fail, but all I'm saying is if you fail, don't worry about it. A life will take you to a different level if you are really focused and if you know what you want to achieve. Um, that's enough about me. I guess we'll start with data engineering. So what is data engineering? So from the data science hierarchy of needs, you could see there are two key area at the bottom where um, reliable data flow, infrastructure, pipelines, ETL, structured and unstructured data storage. So in layman's term, if you have any kind of data that needs to be transported or transformed, then you need a data engineer. Say, for example, you have data in the hard disk and you need to move it to a pen drive. And if you just go and copy and paste it, it is a simple data engineering. So that's one part of it. The second part is cleaning the data and finding anomaly, and also looking at data quality. So this would be the second part of data engineering that we would be focusing on today. So how does data engineers differs to data scientists and software engineers? So when I was in my high school, one thing I really, really wanted not want to do was software engineering, but I studied computer science engineering in MIT, and then I became a software engineer. But eventually, I moved across from software engineering to data engineering because you wouldn't really be coding on the same level as a software engineer would do. Say this is particularly really good if you don't really like a very strong technical background like Java or hardcore PHP or HTML. So it's more like if you're good with data, and I knew I was good with data with because my favorite subject in during college was DBMS, and my favorite programming language was SQL because it was straightforward English. So I think if you are not really interested in software side of things, you can definitely build a career on data engineering side of things, and also being at least part of a data scientist. So with respect to software engineering, you'd be coding mostly on to develop an application or to create a website or to create a backend programming, those kind of things. So mostly you'd be using a scripting language like Java or Python. Whereas in data science, you'd be using lots of algorithms, trying to understand the data, use lots of data modeling, add lots of statistics into it, try to find story which is hidden under the data. However, data engineer is kind of like a bridge between them. So we collect the data from the software engineer who creates the front end, and we do some kind of transformation, and then we pass on the data to data scientists. So data scientist would be one of our clients if you're a data engineer. So the other clients would be a data analyst, or it could be a business users, or it could be someone who wants to visualize the data. So it just simply a bridge between the tech people as well as the business side of things. So it connects. You pass the information, you transform the information according to what the business needs, and then they would be able to visualize and say how the business is doing. Next slide. So the key data structured data, unstructured data, and semi-structured data. So in structured data, it could be a basic RDBMS, just a table. If you have an Excel table, if you have a CSV table, or if you have any kind of like Oracle table, so they all come under structured data because it is you have rows and columns, and the table have a schema, and you know what to do with the data, and you can query it easily with SQL. A semi-structured data is you don't have a schema, and you can have a hierarchy, which I will explain you at the end of the presentation. And you are it's something like JSON or XML. So you have a keys and value pair, and you try to extract the data based on the key and value. Mostly, I don't think you would be able to use SQL for that. We have no SQL at the moment, which does the job for us. And we also have Python or other scripting languages which would pull the data from the hierarchy. Sometimes it can be a bit tricky because when you have an hierarchy level, which means you have three tables that can be pushed or squeezed inside the semi-structured data. So you can unpair them. You can gently remove them separately and keep them as two separate tables. I will give you an example. I have a sample work that I did recently, so I can explain it with that one at the end of the presentation. And then the last one is unstructured data, which is audio, video, Internet of Things, and geospatial. So these data sets are quite like you need special tools to read them, and it depends on the data set. Multiple hats of data engineering. So that's Owen Morgan. If you guys don't know cricket, he's from Dublin. So the data architecture is the one of the key areas of data engineering. So what we do is so we module the whole overall flow of the data. Say if the data needs to be sent from point A to point B to point C, what we have to do is we need to look what data we're gonna send. So if we're gonna send the whole data from point A to point B, you just put a pipeline and send the whole data. If point B to point C, you don't want to send the whole data, you want to send only a view of the data, probably just 100 lines, then you need to add on a filter. So in that case, how you change the data, and it also depends on how you model the data. So data architecture plays a vital role in being part of the data engineering, and it is good to have the understanding of data structures and algorithms, try to understand how the data is stored into a database, and identifying file types that you need to be stored. For example, if you're storing data in CSV, how much space it will take in the data in the hard disk against, let's say, a Parquet file format, which is a binary storage, and it will take very, very less than what a CSV would take. And also the compression types between Snappy, gzip. So this kind of understanding on how the data is stored in the hard disk, how much space it's going to save, it is directly affecting the cost of a company. So, for example, in my company, we are very small, Eagle Alpha, and our business is pretty much collect data from all over the world. We have like more than 1,000 vendors, and then we sell them to big financial institutions, and they will try to find alpha in the data and try to invest into stock market accordingly. So in our case, I need to identify the exact file format so that it'll reduce the cost of storing the data. If I choose, say, CSV, and for 10 terabytes of data, if I pay, let's say, $200 against, if I do it with Parquet for $50, that's like $150 for one data set. So yeah, data architecture is very vital when it comes to data engineering. ETL and ELT, they both are pretty much like business usual. So you pretty much collect requirements from your clients, which would be a data scientist or data analyst, and process the data. So there is a difference between ETL and ELT. So in it, you collect the data, transform the data, and then you push it into data warehouse. Whereas in ELT, you collect the data, throw the data, doesn't matter if you process them or not. You usually throw them as a raw data. You wouldn't do any modification. So in the data warehouse, you always have the data in the raw format, and when and if needed, you extract it, you process them, and then you push it to the client or the visualization tool that you want to play with. So mostly in ETL, we use data warehouse, whereas in ELT, you use data lakes. And ELT is kind of fairly new. It came in 2010s, so it's been there for 10 years. Well, it's not really new, but if you compare with data warehouse, which has been there since 1980s. So, and the last one is DBMS and cloud and DevOps. So having basic understanding of how a database management system works, and we also have latest technology with MongoDB or DynamoDB, where you read a file and you don't really have data in a structured format, but you still process them. With everything has moved to cloud, so I think I don't know how the because when I was in MIT, there weren't any cloud, so that there is no textbooks on cloud. I'm sure they might have changed it by now. So cloud is very, very key and important because most of the businesses have moved to the cloud, and it is like our company, we have around 20 to 25 people. We are a small company, and we have absolutely zero servers. We don't have everyone have a laptop, but no one has there is no company server because everything is on the cloud. So I think that's what most businesses are doing at the moment. Everything is in cloud, so understanding key companies like AWS or Azure or GCP is vital for any kind of IT. Could be software engineering or data engineering or being a data scientist. It's all very important to have a good understanding of cloud. With respect to data engineers, DevOps is quite, sometimes we might need it because, especially if you're working in a small company, if you have to give access and permissions to someone else, you need to have an understanding of how the permissioning works, how the giving access to another user's work. So, and it could be internal within the company or external to the clients or vendors. So you need to have a basic understanding of DevOps as well. So having said that, those are the multiple hats that a data engineer would have. So here, evolution of data engineering, I think I'm going to spend some time in this slide because this is one of the key areas where we need to have an understanding. I'm a big fan of history, so it's good to understand what happened in the past and how it has slowly changed to where we are at the moment. So in the 80s, database were kind of very important, and for banking systems, it wasn't really big with the other industries because they weren't using much computers. So in financial and bankings, databases have become a big part, and then it slowly started spreading across other industries. So when I started my career in 2007, it was mostly RDBMS, which is Oracle databases, and or a SAP database. Everything in one area. We don't really have any kind of what's called the fact table or dimension table. I'll get you fact table and dimension table shortly. So it's all like one master table, and you have a historical table. So I used to work for a retailer, and if you go to a retailer in India, for example, Reliance, if you scan a can of Coke, it collects the information, it pushes to their Reliance server, and that's it. There is no kind of a big database where it stores the data for analysis. It'll be in the master table for probably a year. They ever had in 2002. And then it started slowly changing where people divided the master table and historical table. They started building more on historical table, probably 5 years of data just to understand what happened in the history, try to analyze. So in the historical table, usually it's large and massive. So we need to denormalize, perform some kind of indexing with the databases, and it was always difficult one to collect the data or analyze the data, especially if you want to join that massive table with other tables. It sometimes, like most of the times, it won't really work. So I totally see where the problems were, and big companies wanted to move on from there, and they started building data warehouses. So with respect to databases, in the first one using SQL, PLSQL, the data is usually stored in batch processing with very tight SLAs, service level agreements, where you need to have the data by end of the day. So for example, in the same example of the transaction, if you buy something in Reliance, you wouldn't really have the data in the database in the very next second back in the days. They collect the data, store it locally, and then they push it to other tables. Say, for example, if the data has to go to historical table, they run a cyclical batch job, say every hour, and it'll every hour the program runs and collects the data. It's the same method. If you go to your online banking, you made it, you collected money from an ATM machine, but the transaction wouldn't even have happened in your online banking when you check in your phone app. It's because they're just gonna take some time, 5-10 minutes, or some banks would take 1 or 2 days to upload the transaction into the phone or into the database. So it's yeah, the batch processing is not instantaneous, and you also always have schedulers and cyclical processing in order to perform the transactions. And then came the data warehousing, where you have OLTP and OLAP. So OLTP is the transaction processing. If you perform a transaction, it goes into a master table, whereas OLAP is an analytical processing where you build a database based on facts and dimensions, which we will look into in the next slide. In this case, you integrate the data with tools like SSIS, Informatica, and there are lots of like integration tools in the 90s. Um, and you collect the data from the systems and you push them into the warehouse, and you use it only for analysis purposes. You don't really touch them for, and you have your own transactional system separately and your analytical system separately, and your transaction systems would have only day-to-day data, so it'll be quick and fast, whereas your analytical data warehouse would have loads and loads of data, probably for the last 10 years or 15 years, and they analyze it. I'll give you a quick example. This is like an example from probably from the Nordics. I don't know if you guys know about Tesco Superstore in the UK. So Tesco used to collect information about customers when they use a club card, and so one of the customers of Tesco, a woman, she received a letter, and her husband opened the letter, and it had all the products, pamphlets for baby products. So he went to his wife and asked, "Are you pregnant? Why is Tesco sending you all this baby products information?" And the wife said, "Yeah, I am pregnant." So it's Tesco knows before the husband know that his wife was pregnant, because it collected data from the wife, something like if she have a folic acid tablet, or if she takes some kind of immune boosting, then with the age range and few other algorithms, they can identify if someone is pregnant or not. So these are like a classic example that we always use in the masters, to understand how you can manipulate with the data, understand a customer's behavior. So in order to do that, you need to have a very big history of what the spendings are, and all those history cannot be stored in transaction um, and the data there are the data warehouse is pretty much centralized, and it uses ETL. So you transform the data before you push it into data warehouse. There is also lots of challenges within data warehouse. Sometimes you have way too many dimensions, and sometimes the data can be in different format, like a JSON or XML, and processing them can be a nightmare with the data warehouse. So, and the other reason is why we moved to big data was the size of the data, which in the likes of Facebook and Amazon, the amount of data that we receive is like few terabytes per second. So the constant incoming of data, like even data warehouses cannot handle it. So we need to have distributor systems in various clusters to process data. If I need to process, say, 1 petabyte of data within like 2 hours, I definitely need loads of clusters of systems, different nodes, and process them in parallel and then merge them together. And that's when in around 2006, we had MapReduce that was introduced in Google, and eventually it was moved on to Apache. So MapReduce is very big for big data. It runs in parallel. It's very distributed in large clusters, and it's very time efficient. It can process lots of data in a small amount of time. And then along with those things, we have data pipelining tools eventually started coming out, which is like In Facebook, they introduced Data Swarm, and then being inspired by Data Swarm, which is a pipeline tool. Airbnb introduced Airflow, and Luigi was introduced by Spotify, I think. So these kind of data tools helps to pipeline the data, which set of data has to go where, kind of having a complete flow of the data. I will explain you about data pipelines in the next slides. And the next one is rise of Python, which is Python has been there for a while, but since the emergence of big data, Python has taken to a different level. So it's very key to having an understanding of Python, especially when it comes to big data, because most of the companies have sometimes Java, but most of them have Python as the backend for big data pipelining. Um, and then the real-time cloud serverless, as we spoke earlier, most of the companies have moved to cloud. With At the moment, we have lots of streaming data, for example, Twitter stream or real-time data for a retailer. They use lots of Spark and Kafka for streaming purposes. Um, and cloud systems like AWS, which came in 2006, and Azure, GCP, even Zoho in India have a good base, IBM. So all of them have slowly moved to cloud. Like that's pretty much what Oracle and SAP had missed out. If you see in 2000s, most of the market share on databases were taken over by Oracle and SAP, but because their inability to move to cloud systems or lacking in innovation, companies like AWS and Microsoft have moved so quickly to cloud systems, and they pretty much took most of the market share. Um, so what are the great things about cloud is one of the big thing is you can access the data any part in the world. So at least one of the servers will be available, and you can also perform automations using serverless, something like AWS Lambda, where you don't really need a physical server for yourself. It can be a server allocated within AWS, and they will let you to use it for free. It'll be kind of like a shared service. So in this serverless case, like you don't really spend any money on the server, whereas your job will be computing will be performed by AWS. So it helps quite a lot for automation, running data pipeline in the backend without paying any money. So that's one thing which is kind of trendy now, serverless. And the last one is Athena and Glue. There are like crawlers data visualizing tools available in the cloud as well. So it's so easy for you to connect instead of having an app for everything. So you don't have to download an app into your system every time you want to perform something. It's all available on the cloud, and you can just open their website and start processing the data. The last one is where we are currently at the moment as an the current trends and the future trends. So Lakehouse is the next level of data, big data, from data warehouse to big data. I think it's gonna go ahead with the data lakehouse, which is pretty much a combination of data warehouse and big data. And it enables lots of business intelligence and machine learning to be processed using in-house. So that's something, the new terminology that's been sticking around for 2020. Auto sensing is another area where the current trends are going. If I have if I have a file, it need not to say what kind of file it is. So I just need to have a machine that will automatically understand the data, read it, and process it, and gives an output. So pretty much what I do. So if this auto sentence comes in, probably I may lose my job. So that's pretty much what some of the companies are trying, automating the entire data flow using auto sensing. AV is one area where data is used quite a lot. Autonomous vehicles, where that's one area, from Google to Apple to Tesla, everyone is focusing on autonomous vehicles. So mapping using geospatial data and sensor data. It has to be real time, really quick. There are loads and loads of data challenges in this area, and this area is it's really hot at the moment. So probably if you chat with auto guys, probably they might understand. Obviously, machine learning is another one. It's been around for a while. However, we still have lots of progress to be made on this area. So these are the current trends, and where I think the future is heading towards with respect to big data. So, as I mentioned earlier, data warehousing concepts, it'll be good to understand the differences between OLAP and OLTP. In OLAP, it's an analytical platform where you put all the data into. With OLTP, it's only transactional, so you only have the current data. There are a couple of, so if you look at this particular cube, sorry, just move this to the other screen. Okay. So if you look at this screen, you would see, so this is most of the data is stored in cube format, as in not physically, but logically. So you would have one particular table for a dimension for time, one dimension for the continents or the countries, and one dimension for products. So you can have multiple dimensions like customers or vendors or cities. So you try to connect all these dimensions to identify one point in time what happened. So you have a fact table which will contain, let's say, how many TVs have been sold in Europe in Q1 2020. So this will give you this particular piece of information, and this cube will give you how many um, TVs have been sold in Europe in Q1. So that how many, that particular number is a fact. So that comes into the fact table, and rest are all into the goes into the dimension table. Or that could be another example, like how much money I made using um, tablets in Asia in Q2, which would be tablet Asia, and Q2 is this one. So this will give me how much money made. So those facts are the numbers that will mention. It's called a fact, and it usually sits in the fact table. So in data warehousing, this is the whole area that we focus on, how to build a cube, how to build, how to do a modeling for the data that we currently have in a way that we would be able to identify the business needs. If a user wants to understand how many laptops have been sold, I should be able to collect the data and process it and give the information quickly. So there are two key schemas in data warehousing: star schema and snowflake schema. So in star schema, you have one fact table, the middle table. This is the this one has all the numbers, how many products have been sold in a particular day, on which product, which location, and this one is a dimension table which contains product ID and product details. What's the origin of the product, who is the supplier of the product, and then you have another one called, let's say, country. Let's say India, it's in Asia, and what are the cities available in the dimensions, and the other dimensions could be the time. So it will say what is Q1 2020, from January to March would be Q1. So all those informations are stored in the dimensions. In Snowflake schema, it's more or less the same, except that the dimensions table will have further dimensions. So here I told you about the products. You have a product, let's say a laptop, and you have a vendor from China or India who is manufacturing this laptop, and they will have the vendor details in the further dimension table. So this looks like a snowflake, whereas this looks like a star. The difference between these two is normalization. So the data are stored in different norms. So it'll take furthermore technical, but if you guys are interested, you can make a note of star schema and snowflake schema, and you can search it yourself. There's lots of things available on this one. So these are all key aspects of data warehousing. And then you also have Galaxy schema, which is having multiple fact tables. So within one data warehouse, you have two fact tables and then multiple dimensions connected to the fact tables. And the last part of this one is data marts. Where you have one segment specifically allocated for a data warehouse. Say, if you have a big company like Reliance, you would have a data warehouse only for their retail in Chennai, and then you have a data warehouse for retail in Bangalore, something like that. So, um, um, or maybe channels, you might have online shopping or um, in-store shopping. So if you want to keep them separately, you can build a data mart for online shopping and build a data mart for in-store shopping, so that they are in two different parts, and you can build an analysis on those data marts separately. So it's pretty much like segmenting an enterprise. So that's sorry, trying to get the next screen. Okay, so the key big data tools. So what is big data? It's a question that's been there for a while, trying to understand when the data becomes big data. If I have a CSV file, um, is it a big data? Or if I have a file that is probably say 20 GB, is it a big data? So I constantly get these questions from vendors who don't really have technical background, and they have set of data that they want to sell, and they come and ask me, I have 1 terabyte of data, is it big data? So like the common understanding of big data is like large amount of data is big data. It's not necessarily to it's more like there are various aspects within data, like how much, if it is a recurring data, how much amount of data is coming through, and what is the volume of data currently, and what's the variety of data. So there are lots of, I think there are 6 or 9 videos that are will help to make a decision on business. So this particular area, big data, it's been there for a while. However, it's been really up and running since 2006, since the introduction of MapReduce. The tools that are available. This is another slide. I would be taking some time because I really want to explain you about these different tools, what they do. If you want to make a note, and you can Google it yourself later on, because these tools are used on day-to-day life in most businesses. And these tools are key big data tools, and they are pretty much like if you're good at one or two, it'll be easy for you to build a career in this area. So the key one at the moment is Apache Hadoop, which is kind of like the hardcore distributed file system. So it stores data sorry, it processes data in distributed systems. So instead of processing everything into my same machine, having a high computation, I share it with multiple clusters, and it uses an algorithm called MapReduce. I don't know if you're introduced to MapReduce. It will in layman's term, it will map all the different variables, and then it will collect the information as a fact. Say, for example, how many words are available, um, um, which contain the same. Say, for example, in this one, we have Apache is one, Hadoop is one, whereas you could see multiple Apaches. So Apache is going to be one, two, three. So it maps the individual words into and makes a count, and then it reduces it at the end. So it's a very long, it's a lengthy technical algorithm. So if you guys want, you can Google it yourself. I think it'll go a bit technical if I start explaining more on that. Um, and so Hadoop has been there for a while. They didn't have much competition for a while anyway, and most people were using this particular piece of application because it was an open source and it was free. But the heart of the Hadoop, which is MapReduce algorithm, that's pretty much is that framework is used pretty much across various um, tools like Cloudera, because that's the framework that is built for big data, and I don't think there are any other framework that is currently available. Um, so yeah, probably you can look for Hadoop and MapReduce. And with respect to Cloudera, Cloudera is one of the reliable big data tools for performing um, computation. So when I say computation, it's about, let's say I have 50 petabytes of data coming in every day from a source. I want to do an aggregation, so I need to add up all the product details, how many of them have been sold in say, let's say in the case of Reliance example, I want to see how many TVs have been sold in Chennai Reliance, Bangalore Reliance, Delhi Reliance. So in this case, I need to do a summation of every individual transaction happened in that particular place. And if I have to do it for like 50 petabytes, it's going to take quite a long time. So that's what Hadoop or Cloudera performs. They divide it and they compute it, and then they give you the final table with the summation of product, how many products have been sold. So having said that, with respect to Hadoop, there are like multiple modules available. Something like Hadoop Common, which contains libraries and utilities. So there are like 4 different modules, key modules. Auto is something that manages and schedules the jobs, and it's a resource negotiator. So if you have multiple clusters, it allocates how much data or computation has to be given to which cluster. So it manages multiple resources that are in Hadoop. And we also have Hadoop Ozone, which is pretty much introduced in 2020. It's an object store. And we also have MapReduce. So these are the modules that are in big data. And with respect to Cloudera, it is kind of came up recently. It is much faster than Hadoop, and it is very reliable, and it is open source as well. It is built by Cloudera themselves. Um, and it can deal with a large amount of data, like larger than what Hadoop would do. So it if yeah, so I can't exactly give you your numbers, but the performance, what I've been reading and I've been told, is the performance is better than Hadoop. So Cloudera is lot more reliable and easier to access, and they are in all the cloud systems from AWS to Azure. So that's second part, and the other thing is you can also um, sorry, the on Cassandra, that's the third one. It distributes large volume of data. Sorry, I'm just trying to understand my notes here. So if you have a very large volume of data across various servers, I think Cassandra helps, especially when you have a cloud system in US and one cloud system in Japan and one in Europe. And if you want to process data in multiple regions, Cassandra seems to be performing well. MongoDB is mostly used for doing a NoSQL. If you have unstructured data, it is really good to process the unstructured data using MongoDB. In AWS, they have something called DynamoDB, and it's more or less the same. Apache Swarm is pretty much a recent one. It is used mainly for performing real-time data and real-time analytics, and they I think it just came. The stable version actually went in 2020, and it's been created only in like 2018 or something. So it's fairly new, Apache Swarm. And then we have our old friends Hive and Presto. So Hive is distributed data warehouse where you could store data as well as query it with SQL, like ANSI SQL or just normal SQL that we use. It's been built by Facebook, and it is open source at the moment. Loads and loads of companies actually use Hive because it's very easy to access. Even sometimes business users, like people who do not have technical background, can access Hive. Presto is just a SQL tool for accessing data from Hive or from any other databases, data warehouses. The Presto is really quick. So Hive is used mainly for computation. So if I have to run not too big, not too small, it's kind of like medium style, let's say 100 terabytes of data every day, I would rather go with Hive and process them using Hive, store the data in Hive data warehouse. And Presto could be my front end where I can run a query to see the data, because it wouldn't take too long to return the data. And then we have Apache Spark. Spark is mainly like, this is another trending tool at the moment in the industry, Apache Spark. More and more companies have started using Spark. So Spark is pretty much faster than it is really fast because it's in-memory processing. So they don't process anything in the hard drive, they process everything in memory. So it's kind of like 100 times faster if it is done with in-memory, and 10 times faster if it is done on the disk. It is really used mainly on the machine learning area, especially if in autonomous vehicles. If someone wants real-time analytics and processing data very quickly, Apache Spark is the tool to go. Kafka, again, another new tool for processing streaming data. So if you have a Twitter feed or Facebook feed that are placed within your website, if you want to stream any kind of data, of Kafka is tool to go. So these are sample big data tools. I myself wouldn't be working on some of them. I pretty much work on Hadoop, MongoDB, Hive, Presto, Spark, bit of Kafka. But it's just like you have a variety of tools available in the market, and if you start trying to understand what they do actually, that'll be the first step to go ahead. And probably if you think you want to learn something like Spark, go ahead and start doing a crash course and do some case studies, and I'm sure you would excel. The next one is data architecture. I'm just gonna check on the time. Okay, so we have two sets of data, which is homogeneous and heterogeneous. So homogeneous data is in a big company, you have a finance coming in, and if a sales had happened, it's the same set of data that is flowing from A to B, whereas heterogeneous data is data data that we do in Eagle Alpha in my current company. We have thousands of vendors. They send the data, and we may not get the data again, and it's all different data every time they send. So um, in the case of Reliance, you can understand the schema behind it because you would have it's an internal system. So if your developers are building online shopping, they're gonna tell you what are the data that they are collecting, and you can build a schema based on that. Whereas in heterogeneous data, you absolutely have no clue. It could be a vendor sending the data, and they send different data every day. So you don't really have a schema to automate it. So that's slightly different to what big banks would be getting. Um, and the other thing is recurring data, once of data. So in recurring data, you would be data would be coming on a mentioned frequency, say every hour, every day, every minute. Once of data, probably they ship it once and that's it. So again, it depends on the business needs. In the case of Reliance example, you don't really need them. Whereas in my company, there are so many vendors who would send, say, 10 terabytes of data, and that's it. They would never come back again because that's all the data that they collected. And if they wanted to send it to a company, sell it and make money out of it, and probably they'll move out of business. So it totally depends on the use case of the data. But these are the things that you need to consider before architecting the pipelines. Um, like you might have heard of 6 V's of big data before: volume, variety, velocity, veracity, value, and variability. If not, it's like it's available online. You can check it. I don't want to go deep into each of them. I think we saw some of them like variety, structure, semi-structured, and velocity, and volume. And they also added a few things like visualization, viscosity, virality, which is viral material. I'm sure my name starts with VD, so I could also add a 10th one. So it's just like the first six are key, and then they're just building up. I would say you can just stick with the first six and try to understand that, and that will help you to, if you ever want to be an architect, data architect, that'll be the key things that you'll be looking for when you're building the data pipelines. Um, Cloud and serverless, this is fairly more on the business side of things. Um, you would probably know that AWS is one of the key players in cloud. They have 33% of the market share, and Azure as 18, and GCP as 9. I got these numbers from I think Gartner, one of the survey companies, and it's kind of fairly new Q2 2020. So this is the market share for this year. It's been Azure. If you see Azure, last year they were like 10% of market share, so they have come up really well. And GCP is coming up as well. So AWS is slightly losing their market share. They moved down from 35% to 33%, because there are more and more companies which as cloud because some of the tools are really good. I'm a big AWS user. I use it for day to day. I haven't used much on Azure or GCP, so I did some research for this presentation on Azure side of things. I can quickly explain you on the AWS tools. EMR is Elastic MapReduce, which is the big data MapReduce Hadoop equivalent in AWS. So if I have to process any data, which is probably let's say 10 terabytes, I usually pull down a EMR instance from the cloud and push the data into it and process them. It is very quick. It is easy to access, and the availability can be issues. It depends on how much you are ready to pay to get the instance. but yeah, it's overall it is very reliable and very good. Athena is a tool where it's kind of like your Excel. So you have a data in the system. It's just more like a front end tool which will help you to query the data. So you go to Athena, select, you choose a table, you use crawler to crawl the data into Athena, and then you can have it as a table, and you would be able to see what's in the data. Um, Glue is used for creating metadata about the data, and it catalogs us the data, and it also helps to crawl the data and push the data into Athena, so that you would be able to see what's in the data. Let's say you have a very deeply nested JSON file which has come to you, and you have no idea about the data structure, what's available in the data, what are the data types involved. So with Glue, it automatically senses the data, and when it collects, and it will create a metadata, and Athena reads that metadata and creates a schema. And when you do a select chart from in Athena, you would be able to read that JSON file as in like in a table. So it's those tools are really key for data engineer, and I pretty much use them day to day. DynamoDB, like I said mentioned before, it's a NoSQL tool which is used for unstructured data. S3 is our storage where you store all the files. Redshift is a data warehouse system. You will have multiple clusters, and you would store all the information in this area. Kinesis is used for streaming data, real-time streaming data. Lambda functions serverless, so you could, if you want to automate something, you could push. You can push your code to Lambda using Python or Node.js, and you can perform some kind of computations, and it will throw the output into your S3 bucket if you let them let it that way. You can also um, call a program by what you call them, triggering is a key functionality that is really good with Lambda functions. So if you have a file coming into S3, you can trigger a job to run and process the data and push it. So it'll be done right there, instead of doing it in a scheduled manner. IAM is the access, giving access to people, access management. Uh, Letting permissions for your clients or vendors to access your data, or if they want to send you data, you need to give permissions to your buckets. VPC is another one, pretty much on DevOps side of things. So these are the key things that if you're a AWS user would be using as part of your data engineering skill. This is pretty much like key ones. Obviously, there are a few more depending on the company that you work for. With respect to Azure, is that the data lake storage is what where you store your data, and Databricks helps you to crawl the data. And I think Synapse Analytics has kind of came very recently with Azure, and they help you to visualize data. They pretty much Databricks to it's kind of like a combination of multiple tools together into like one studio where you perform everything. And Power BI is pretty much used for visualization. Probably you would know with they are the biggest competitors of Tableau. So, and with respect to GCP, BigQuery is where you store your data. Data transfer helps you to transfer the data, as the name says. Data flow is your pipelining system, and Dataproc is sorry, I just yeah, it's your EMR. That's the Hadoop and MapReduce, where you process the big data using Dataproc. Um, Data Fusion is used for ETL, and Data Studio is mainly for visualization. Data Science with a reputation. So these, as I mentioned, I mainly work on AWS. I haven't really had much experience on Azure or GCP. However, if you're in cloud, you would constantly research on these areas, because if say I could be on AWS, but my client could be on Azure or GCP, and if they want the data into their cloud system, I need to have an understanding of other clouds to transfer data. So cloud to cloud data transfer can be tricky. You would always be have good knowledge on AWS, but you if the client is on GCP, you need to force yourself to learn GCP to transfer the data to them. And also there is lots of with respect to cost, the lots of things like you usually pay for pushing out the data for your storage, obviously, but you pay for data transfer when you push the data out of the cloud from AWS to Azure. You need to pay AWS to push the data out of AWS, whereas Azure wouldn't charge you anything to get the data in. Same with all the other clouds. So if someone is sending me data from GCP to AWS, people would pay GCP to leave the data, but they wouldn't be paying anything to AWS to collect the data. So it's usually whoever is letting the data go has to pay the company for transferring data for leaving the cloud. So that's pretty much on cloud. We did talk about serverless with Lambda. Data pipelines. So simply, it's you have a pipeline for each processes. So every task, let's say this is the time period where August 9th to August 30th, and the green one marks if it is completed, the red one marks if it is failed. So let's say you have a task one where you have 1, 2, 3 steps, and then second task with multiple steps. So it's pretty much like hierarchy. So if this job runs, the send SNS notification, then the check starts run and aggregation runs. Whereas this one, the send SNS notification and email notification are parallel, so they can run at the same time. Whereas the generate new Parquet files would run only if the previous job runs. So it is based on dependencies on the previous job set. So the overall idea is that this is a pipeline and this is a pipeline. So there are like eight pipelines available for the route, and each pipeline would turn green when they are completed. And if one fails, you can try restarting them, or you need to find why it failed and you fix them. And then once you fix them, the next pipeline will start. So Airflow is one of the big companies, open source. You can download Airflow. It's free, and you can run it by yourself. So it's fairly easy. So business intelligence, we're not going to spend much time in this area. So with business intelligence, the reason why we need business BI is understanding what the data says, the story, and making business decisions, and what are the problems that are available, and visualizing the data that are collected. Areas that we BI are dimensional facts, one of the areas. So you can slice and dice. So when I say slice and dice, it's going to be like slicing the data for one particular period or one particular product, and you can roll it with multiple. You can dice it with multiple other dimensions that are available in the schema. You can do data rollup like aggregation, summations, and you can do data drill down. So if you do a summation, let's say in Tamil Nadu, we have 450 TVs have been sold. You can drill it down to a city level or even to a town level to identify where it is being sold. and having a source of truth, which is important, because when you have multiple data sources, or like same data is coming from two different sources, it's very hard to identify the truth, the actual fact. So business intelligence helps you to do that. Reporting and dashboards. So if like if you're a CEO or a CFO, they don't really care about data. They all they need to know is the dashboard. They just click on it. They want to see how much has been sold. They just want to see everything on a larger scale, on a summarized level. So to perform to that summarized level, we will be doing lots of computations over the course and build nice dashboards. So all they have to do is click it, and the number shows and says, we sold 450 TVs in Tamil Nadu. The sales is going well, so probably we can focus on further on TV, or not to focus further on TV, something like that. So the business decisions are made based on the real data, and we would be a key part in providing that information. And data analytics, this area is pretty much does what the reporting and dashboards does. Also, it will check in the example that I gave you with Tesco, checking the customer data. Data analytics performs all these things. So there are lots of data analysts who will go and check if there is a problem with the data, if they can do anything. Say, for example, if you are using a credit card, if there is a fraud in the credit card, they try to identify before the fraud actually happens. So in JP Morgan, in the credits in the payment section, if you have we had data analytics team working on identifying frauds in, say, if there is a particular country known for fraud, or particular town known for fraud, then they would make sure that the fraud didn't really happen. If a transaction goes, and if it is speculative, if they think if it's going to be a fraud, they have an algorithm to do that. They would stop the transaction. And to make sure that algorithm runs smoothly, we need to know we need to have a set of data to build the algorithm. So data analytics team actually performs that. So they would collect the data. They would see, okay, which countries are the countries that are high amount of fraud, and which particular locations have a high amount of fraud, and what are the tricks that a fraudster use. So they collect the information that are available in the data warehouse, and they pass it on to the next team, who would build an algorithm to prevent the fraud. In the case of JP Morgan, obviously you can, like for each businesses, you can analyze the data and build algorithms depending on your business case. So that's pretty much it. Real world problems. This is a problem that I encountered last month. This is semi-structured nested JSON data. So you would have a multiple hierarchy. So if you look here, this is a table called order. Within order, you have an order number, date, and customer. And under customer, you have a different hierarchy named customer ID, name, and addresses. So you can also have further, if you want, for the hierarchy or for the drill down. So converting this kind of data into, you can obviously read it with it's easy to process with those ones. But when people ask you to convert them into Parquet or any other file types like CSV, then if it is a massive file, like I think this file was around 10 terabytes. This is not the actual file. This is a sample file that I got it from internet, but the file would be something similar to this, and I cannot share it for confidentiality reasons. So this sample file would be more like around 10 TB, and to process them, I definitely need a EMR, but I need to have a background script like Python, and I have to do a self-recursive function in Python in order to read. So this itself contains two tables. um, the order table which will contain all this, and a customer table which will contain all this, and there'll be a foreign key that will connect customer table on the order table in RDBMS. Whereas in JSON, you can all put them into the same file, and it'll still be okay. So this kind of nested. So this is a simple sample example. The actual file had a lot more hierarchies and a lot more deep down. So you have a dict to list. You have multiple lists inside a dict and multiple dicts inside a list, and it'll go on. So I have a self-recursive function in Python to perform it and separate them into two different tables, or whatever number of tables it has in the file. So this is what it will convert it into. So the order will have order number, date, and customer ID, and the customer table will have this one. So the foreign key is the customer ID, which will connect. So you can split the JSON file into two different files, and this would be pretty much a job of a data engineer. So I don't think a data scientist would do this, or a software engineer would do. Like obviously, if they're skilled, they would be able to do it, but this would be a day-to-day business as usual kind of task for a data engineer. Um, and the file formats and compressions, usually people ask for Parquet, ORC. So Parquet is a columnar database where you store data, collect the data in a column level, whereas Avro is a row level data, stores data in row level. And you have the usual culprits, CSV, TSV, XLS, and JSON. So these are the key formats that I've been using in the last few years. And then compression is kind of tricky. You need to have a balance between the read time and the storage. Say if you take gzip, it compresses very tightly. So if you have a file of 1 GB, it'll maybe bring it to 750 MB. However, the read time is really, really long. So because it compresses very tightly, it takes so long to read through it, to unpack it. Whereas if you take Snappy, it may compress slightly loosely, probably around, let's say 950 MB or 900 MB, but it reads very quickly. So if you have to process data very quickly, and if you are happy to pay the extra bit of money for the storage, then you could use Snap. So again, it all depends on your business case and the project case. So these are the multiple compression types and file types that I've been using lately, and this is pretty much available in most companies. So that's it. With respect to BI, I can quickly talk through some of the case studies that I went through. Say, for example, where the business intelligence is used. Let's say I have a website. Even in my company, Eagle Alpha, we have a website where people come and visit the website. The clients sometimes page navigate. They try to find something. They go to the search box, try to search something. It's not there, and they just leave the website. But this, if we get this information, if we try to understand what the client tried to search for, and if maybe it is not there, but we can procure it and give it to them, it's a sale for us. So in order to do that, we need data. So our software engineers collect the data, people who visit the webs and where they navigated to, what are the things that they try to search for, and our data analytics team, which will eventually put all this information in a way that our sales team can read. So there'll be dashboards and stuff. So you go and click this dashboard, it'll say, oh, this particular client tried to search for ABC vendor, but ABC vendor is not giving us data anymore. Probably we can go and chase them and see if they want to share the data with them. So, or maybe go back to client and send them, hey, ABC is not giving data anymore. Do you want to try XYZ? So it's just more like understanding the client, their needs, what they're trying to look for. They need not to speak directly to us, but if they we could understand them. Like you would have seen this if you go to Tableau and try to put your email and try to access few things, they would come back to you asking, "Hi, I saw that you are trying to access a document. Do you want any help?" So sometimes people say yes, and then it's a sale for them. All they need is sale. So BA can be used on that one. And I worked on this particular one, task perform by individuals and teams in Facebook. In Facebook, we follow the sun model. So we had three teams, one in Singapore, one in Dublin, one in San Fran. All these three teams work 8 hours a day, so 24 hours a day during daytime, their individual daytime. So my boss was kind of to know who is performing well. There's always kind of chaos of this team is doing well, this is not doing well. So I brought in multiple data sets. I called the team names and individual employees within the team, build up a dashboard where using Tableau, where people can click on the continent and they can see how many tasks have been created in a particular time period, and they can drill down to see up to individual people level to see how many cases they fixed, how many projects they completed, those kind of things. So it helped the boss to understand which team is doing well and where they can improve on. So this is another good example of business intelligence. And the chargebacks and frauds that I spoke about earlier. So that's another use case for BI. So this is just a real world problems that we fix in the business intelligence side of things. So what's a typical day a day? So just so we're in the last two slides, just want to keep it in a lighter note. So we try to find the problem, we try to fix the problem, and then we'll have two problems, and then we have three problems, because you try to, especially with respect to data, if you make one simple mistake, it's gonna give a massive impact in the data, especially with the data scientists and data analysts. They won't be happy with that. So if you're trying to aggregate the data, if you're grouping by something incorrectly, it's gonna make massive changes. And if those data scientists are unless going to CFO or CEO with the data, and the CEO says, this data is CRAP, it's not really looking that good, then it's gonna hit you hardly. So I think need to be fully focused and try to solve the problems. Yeah, there's always gonna be more and more bugs, and the day actually goes like this, and the day actually ends like this. Every evening you go there, there's always something to do. The work never ends. So yeah, that's pretty much it. So I just want to open the forum for question and answer sessions. If you guys are have any questions.